Okay, so welcome back. So let's continue this chapter, which is about entropy. So I will try to close this chapter today. And the next lecture, we go to the variational principle, and we will stop there after the variational principle. So we were in this chapter about entropy. Okay. So remember, I will recall what we have seen in the last two lectures. So remember, we always have our measured space. This is a measured space. We have our topological space, the Borel sigma algebra, and a measure, a probability measure. And I always assume that there is a dynamical system, and mu is F invariant. S star mu equals mu. And the least condition we have on F is a measurable. It's a measurable map, okay? And remember, we had like a definition of a partition. So this was a measurable partition. So as I said last time, we always consider at most countable partitions, okay? This is a measurable partition. And if you remember, we have seen the entropy of a partition, which is just this, with respect to the measure mu, not yet dynamical system, like there's no dynamical system involved here in this definition. So it was minus the sum along the partition element of mu of p log of mu of p. Okay, you sum up all, yeah, so there's a minus sign here because this is negative and you want this quantity is non-negative, so it may be 0 or positive. And we had an entropy with respect to entropy of a dynamical system with respect to a partition. So entropy of F with respect to P, this was given by H mu Fp, which is the limit when n goes to infinity of 1 over n H mu, this quantity Pn. Pn is the partition you have using the dynamics. Okay, we have written this definition many times, the refinement of this partition. And after that, we had defined the metric entropy, or the measure theoretic entropy. So this is the entropy of this dynamical system with respect to mu. Okay, H mu of F is the supremum of P of overall measurable partitions of this quantity H mu of P. Okay? Yeah. So one thing to keep in mind is that for this definition to make sense, we really needed this guy, okay? The measure to be invariant, okay? And yeah, looking at this formula, this seems something very difficult to calculate. If you want to calculate this, evaluating this quantity for all possible partition is almost impossible, I would say. That's why the rest, after we have this definition, the rest of this chapter was just about to give techniques to evaluate this entropy. So one was given by the Kolmogorov-Sinai and Sinai theorem, which we have seen it last time in the proof also. If you have the partition which is non-decreasing, a family of partition, so this said that this guy is coarser than this one. Think of this one being a refinement of this, okay? Pn and so on, such that the union of Pn, this generates the sigma algebra, yeah, a good example, think about when you are on a one-dimensional, like the full branch map we have been doing, like 2x mod 1, and you see the intervals, and just use this as this P subscript n to be P superscript n, which is a refinement using the dynamics. It satisfies these properties because the intervals, they're getting smaller and smaller, and they will generate the sigma algebra. If this happens, then we've seen that to evaluate the entropy, you can just evaluate the limit of this H mu F P n. Okay. Now let's do some applications of this. I would like to do the applications for the Gauss map, but this also will work for most full branch map you may have the Gauss map. So remember, the Gauss map was g of x equals 10x mod 1. I'm sorry, 1 over x mod 1, sorry, yeah, this is what I want to say. Yeah, so, yeah, if you remember, this is a full branch map. It has a countable partition, and it's uniformly expanding. It has what we call a distortion property. Let me recall that. And also, we have seen that it leaves invariant a measure that is equivalent to Lebesgue. So recall that this measure, mu of E, equals 1 over log 2. So this log 2 is just to normalize to have a probability measure. Dx over 1 plus x is G invariant. Yeah. Yeah, we have checked this. If you want, you can use the Perron-Frobenius operator to see the density as a fixed point of the Perron-Frobenius operator. And yeah, so we want to calculate the entropy of this dynamical system G with respect to this measure mu, okay? Yeah, let me recall the properties of this Gauss map we have seen, which is that we have a partition, which was 1 over k plus 1 over k, for k equals 1. So this is countable, okay? And so if you look at this partition Pn, using the dynamics here, is a refinement of P, okay? Because what you do is just you take this interval, you subdivide it again into countable pieces. We have few properties. One is A. We have seen all of these properties before. So Gn from Pn, from every partition element, Pn is a partition element which is in Pn like this, 2, 0, 1 is a diffeomorphism. So remember, these are like these are full branches. Every partition element will map to the whole space, which is the interval. And B was that the diameter, yeah, this, I don't know if you have checked it, but you can probably check it. Pnx, this guy goes to 0 as n goes to infinity. And Pnx, we have defined this also, is the element of the partition that contains x. And C was a distortion. Remember, this was needed to prove that this is ergodic, okay? Distortion is something important to prove ergodicity of these measures. So what was distortion is that there exists a C positive, such that for all x, y in the same partition element, so if I write P like this, it's just the partition element, and calligraphic P is a partition. Okay. We have g n x over g n y, the derivatives, okay? These are comparable, is less or equals to c. See that this is not trivial, okay? Having this property is not trivial. For instance, if you don't restrict yourself to this partition element whose diameter is small, you don't hope to get this. Because you see that the derivative of 1 over x is 1 over x squared. So you see that the derivative is going to infinity at some point. So this is crucial, okay? The fact that you restrict to a partition element. Also for general full branch map, you always restrict to the refinement of the partition because you don't hope to get this. Because just this quantity here, for full branch expanding map, this quantity here is going to infinity. So you should restrict to this partition element. And also see that if this guy might be trivial in the case that you say, you have a partition element that is very, very small because, and your map is C2 because this by mean value theorem, you can bound it by the C2 derivatives times the distance. So if the distance is smaller than the C2 derivative of this guy, you can hope to get distortion as well. So there is a kind of a balance between how big this can be. Yeah. Here we are not defining how big it is. It is a dynamics which is deciding how big this interval is because Pn you get it from the refinement. And that is a good partition to use if you want to do ergodicity and other properties as well. And D is that mu, this measure mu is equivalent to Lebesgue, okay? Because of, this definition here. You can see that mu is absolutely continuous with respect to Lebesgue, and also Lebesgue is absolutely continuous with respect to mu, and it is this. So this is just to say that there exists C1, C2, such that mu C1, mu of M. Also, I will have to use Lebesgue here. M of E. Okay, so these are. So now the proposition I want to prove is that, that's just calculating the entropy of this dynamical system, which is Cnx. Oh, sorry. H mu G is the integral of log of G prime d mu. Okay, this is the formula of the entropy in this case. So I will first do the proof just using the Kolmogorov-Sinai, but by the end of today's lecture, we will see that you can get it easily also by using Shannon-Macmillan-Bryman theorem that we will prove also today. So let's try to prove this just using what we have there. So let's, just for notational purposes, let's write this, log of mu of Pnx. Okay, this is just notation. So already these properties, the fact that this guy is a refinement here, okay, and the fact that the diameter goes to 0, the fact that the diameter goes to 0 will give you that this will generate the sigma algebra, and those properties allows you to apply, to say that the entropy is given by this. Okay? So by these properties, we know that the entropy is given by this guy, the limit of, for this partition, for this family, this sequence of partitions. Okay, so yeah, so to prove this, we just have to evaluate this limit. Okay? Now, for notational purposes, let's write this as phi n x. So what I'm just saying here is that by Kolmogorov-Sinai, we have that h mu g is limit when n goes to infinity of 1 over n of h mu of Pn. This is Kolmogorov-Sinai because this will generate the algebra, and you have this from the refinement. Okay? And here what we have that if you want to calculate h mu of Pn, this quantity here. Okay. So this is minus, by definition, mu of Pn. Pn are the partition elements, so Pn is in Pn log of mu of Pn. Okay, this is just the definition. This you can rewrite it as, because these are partition, so you can write the partition with respect to, you can take the x's that belongs to each Pn, and you can write this sum as the integral of phi n x d mu x, okay, where x is in 0, 1. Because this is a partition. So every element, almost every element, every x will belong to just 1. Okay? Now here is the time to use now these properties that I had before. Because the measure of, sorry, what did I say? This quantity here, a priori, it might be difficult to calculate, but because of this formula, there's an integral here. But since we are interested in, after taking divided by n and taking the limit when n goes to infinity, we can use the equivalence, the fact that this measure, mu, is equivalent to Lebesgue, and here we can compare this quantity with log of the Lebesgue of Pnx. Because after the constant you would have, you can discard it because you divide by n, take the limit when n goes to infinity, and that is 0. So this is what I'm saying, is that there exists k1, k2 positive such that you have phi n x minus log of Lebesgue of Pnx okay, just using this quantity here, this equivalence of the two measures. So you can see, you can now try to evaluate this guy here when you have Lebesgue here, okay? Now it's observed that the measure, the Lebesgue measure of Pnx is just given by log of so this will be given by, because this is an interval. So this is the length of the interval, and G is a diffeomorphism. So this is what I'm saying. This is Gn prime. So I should write. This is like Gn prime at some point xi times the measure of Pnx. Yes. So let me write it maybe more clearly like this. I can write it better like this. So this is what I'm saying is, from here you can come back to see that h mu is at this quantity here, h mu Pn is less or equal to K1 minus the integral of log of Gn prime x d x d mu x, okay, which is less or equal to K2. Because this measure, you can write it with respect to, because this is the Lebesgue measure, so this is just a derivative by mean value theorem, okay? And if you use the fact that mu is G invariant, so this you can write it as a sum. So this guy here, this integral of log of Gn prime x d mu x. This guy, you can write it as a sum of the integral of log of G prime at Gix, okay, d mu x. So this is a sum I equals 0 to n minus 1. And here, remember, mu is G invariant, so this is just I equals 0 n minus 1 of the integral of log of G prime d mu. Okay, because this will be Gi star mu, which is mu again. So this is what the quantity you get, and this is just n times the same, n times the log of G prime d mu. Okay, and you see that if you divide through here by n and take the limit when n goes to infinity, yeah, you divide through by n, take the limit when n goes here. When n goes to infinity, this will go to 0, so you would have that 1 over n h mu Pn is converging to the integral, because there's this n, so log of G prime d mu. For most full branch expanding maps, you can just see that the entropy will be given by the integral of log of the derivative, and you will see that this will be positive, okay? This is positive, okay? So these maps, they have positive entropy. So there's full branch expanding map, because the derivative is bigger than 1, so log of something bigger than 1 is positive. So I want to give another theorem which is also very useful to calculate these entropies, which is a Shannon-Macmillan-Bryman theorem. So theorem. So this is Shannon, Macmillan, and Bryman. So you take a partition, let P be a partition. This is a more fine, evaluation of the entropy. This is a pointwise H mu P is finite entropy. So H mu of F Px, Px, which is the limit when n goes to infinity of minus 1 over n log of Px. So P and X is the element that contains X. The term, first of all, it tells you that this limit exists. Okay, exists mu almost everywhere. Mu almost everywhere. And yeah, so this is seeing the entropy now as a function on the space, like you have the dependence on X, the entropy of the partition with respect, the dynamics in respect to a partition as a function. And this function is integrable. So the function takes X, gives H mu F P. X is mu integrable. And also this limit exists on L1, so the above limit exists in L1. So this is L1 convergence. So the fact that this exists in L1 mu. And more importantly now, you can see now the entropy as the integral of this function. Entropy of the partition. Moreover, you have that the entropy of the dynamical system with respect to the partition H mu P, F, this function Px d mu. This last statement of the theorem is very close to something we have been seeing in the Birkhoff ergodic theorems. When we were doing the subadditivity, the convergence of Birkhoff sums, so we see that the limit, the integral of the limit is constant when you have ergodicity and so on. So it's along those lines. So we will use the Birkhoff ergodic theorem here at the end of the proof. So applications. So we will see how you can recover so this is easy one, which is 10x mod 1 is easy here. You can see that the Lebesgue is invariant, so Lebesgue of P n x is just 1 over 10 to the power n. So Shannon, Macmillan, Bryman theorem tells you that this function is constant is log 10. And this is, so it is constant, so it will give the limit. So this is H mu Fp. And by Kolmogorov-Sinai, you can see that this is just entropy. So this is Lebesgue, okay? So this is Lebesgue F of the dynamical system. This is F, okay? So let's see, just do again the Gauss map using this theorem. So for the Gauss map, we use this property here. See that the measure of Pnx, so mu is the measure that we had, which is invariant for the Gauss map, okay, is equivalent to, I write this to say that there are two constants. This is the measure of, the Lebesgue measure of Pnx. Then this is, again, like mean value theorem Gn prime of some point xi times the measure of Px. Okay, Px is an element that where x belong, yeah. So this is just mean value theorem, okay? And this is the fact that this measure is equivalent to Lebesgue. And by distortion, we know that this quantity is comparable to Gn prime of x. Okay? So by distortion, you have that Gn prime xi. This guy is comparable to Gn prime x. Okay, here x is in Pn(x), so xi was in, say xi is in Pn(x), okay, for some xi. This is just mean value theorem, okay? This is distortion. Where is that? This here. Yeah. So what you have now is the measure of Pn(x). So what you would have is minus 1 over n log of mu of Pn(x). So there's this quantity here. That is the pointwise version. This guy is converging to log of G prime x. Yeah, this you have it just applying mean value and this here. Okay, the distortion here. You first apply mean value and then the distortion. This you ignore it because you divide by n goes to infinity. So log of this divided by n goes to 0. So what you would have Gn of x, which you can compare with Gx. And this by Shannon-Macmillan-Bryman, this is just the pointwise version of the entropy. And again, you use Shannon-Macmillan-Bryman to see that the entropy of the Gauss map with respect to its invariant measure, which is what we know, is just the integral of this quantity. Okay. Yeah. So Shannon-Macmillan-Bryman is another tool to calculate the entropy. So for the rest of this lecture, we will prove this theorem. We will prove Shannon-Macmillan-Bryman. Yeah, you can, in higher dimension, you can think of, I decided to say it, but I won't say it. You can decide it also to, to check these conditions in higher dimension, because everything I was saying here is just for one-dimensional maps, but you can think of, replacing this quantity here by the Jacobian, which is a determinant of your map, and just about sketch for higher dimension. Remember, for higher dimension, I also talked about a generalization of the parent-Frobenius operator that I defined, and that would also give the existence of invariant measure that is absolutely continuous with respect to Lebesgue. So you would have mu of Pn(x). This guy will be equivalent by mean value theorem. This will be equivalent to the Jacobian of df minus n restricted to xi. Sorry, here I should have, sorry. This is minus n. Why? Because from Pn to Pn(x), you take a minus, Gn minus 1, minus n, okay? Sorry. Yeah. So you have this quantity here. for some xi. So this is the xi for some xi in P and X. And also you can think of having the distortion also in higher dimension, which is a Jacobian of df minus n xi over the Jacobian of df minus n xi prime. This guy is just like 1, so when I write this, I mean there are constants. And that you can have that the entropy of your dynamical system is the integral of log the Jacobian of df x d mu, and mu will be the invariant measure you get when you do the Perron-Frobenius operator, okay? The invariant measure that is equivalent with respect to Lebesgue. Okay. Now let's try to prove Shannon-Macmillan-Bryman theorem, proof of so the proof is quite, a little bit long and very constructive. So so there will be few lemmas that I will need to prove inside this proof. So I will do it when needed. So so this is Shannon-Macmillan-Bryman that we are proving here. So for notation, it's easier to write this function, phi n x is minus log of mu of Pn x over mu of Pn minus 1x. Okay. I think of this quantity being less than 1 because this Pn is a refinement of Pn minus 1. So the elements of Pn are smaller. Think of them as smaller guys. So you have this negative here so that this function will be non-positive. Non-negative, sorry. Okay. So from here you can easy to see that you can add, let me write the formula in first entirely to see that. You can write this, the quantity we want. Okay, let me give myself some space here. You can see that minus 1 over n log of mu of Pnx. So this is the quantity we want to prove. It has a limit. The limit exists and is L1 and all the properties. So this guy, you can write it as minus 1 over n log of mu of P at Fn minus 1x plus. So after when I write this formula, you will see 1 over n j equals 0 to n minus 2 of phi n minus j fjx. So what you do is you take this formula here. You always add n, you always multiply it and divide with Pn minus, you first do Pn minus 1 at f minus 1x. You multiply, divide it, and you will see this sum will appear here, and you will be left with the last term, that is this guy. So you just take this quantity here, you multiply it and divide by mu of P n minus j at f n minus j. Okay? So basically what we are doing here is to see that this has a limit. Okay, this function here has a limit. So let's introduce some notations here. Yeah, so it boils down to studying, this function, the convergence of this function. So some notation. Let's write Qn x as f minus 1 Pn minus 1x. And when you do this, you can see that Pn x is just Px intersect with Qnx. Why? Because the definition of Pn is now you just have to intersect with Px, because you take f minus 1, so you don't have Px in this here. So that's what is left here to have. So remember, Pn was defined j equals 0 to n minus 1, f minus j at p, okay? So, and this is the intersection of these elements. So when you pull back here f minus 1, you kill this j equals 0, so you can see that you have to put it here, okay? And see that p n minus 1 at f n minus 1x, yeah, so this is Qn x. Okay, this is also easy to see, and from there you can easily see that the function phi n x is nothing but minus log of mu of Pn is Px intersect with Qnx over, this is just notation, mu of Qnx. Okay, so we have few lemmas, like 3 lemmas that we need to prove here before we get back to the proof of the theorem. A couple of them are easy, 2 of them are easy, and the third one is more delicate. So lemma 1 is that this guy, the limit exists of this Vn. Vnx exists me almost everywhere. So the proof of this is just you write this function, this functional Qnx times the integral along Qnx c d mu. If you did that, you can see that phi n is nothing but En of the indicator function of Px dx. Yeah, and it is easy to see that this is converging because, how to say it, you have the integral, so you have this set, this is just the mean of this function along this set, so it is easy to see that, so this implies that this guy is converging to some function c, me almost everywhere, because this is just the mean of the function on this. Now there's lemma 2, which is that this guy, the supremum of phi n, is integrable. So this we won't do it immediately. Let's see the other one. Lemma 3 is that this guy is converging to CL1. This convergence that you have here, which was just almost everywhere, is L1. Okay, always L1 mu. Yeah, let's see how to prove 3 from 2 is simple. You just use the dominated convergence theorem, okay? 2, lemma 2 implies lemma 3. So this use dominated convergence theorem, okay? You have that you have pointwise convergence and that these guys are dominated, so phi n is less or equals to phi, which is L1, okay, by lemma 2. So what we have to do now is to prove lemma 2. So let me do the proof of lemma 2 here. So these 3 lemmas are just used to prove Shannon-Macmillan-Brahman. So I will get back to the proof of Shannon-Macmillan-Brahman when I finish the proof of lemma 2, okay? All right, so see that, so we want to prove that this is integrable. So this is a supremum, so it exists, the supremum of n, this exists and is a measurable function. So we want to prove that it is integrable, so we want to evaluate d mu. This is what we want to evaluate. So using the fact that we have a partition, we can do this, okay, because this is a measurable partition. Okay. And this integral here, I can write it using the levels of this function. So mainly I can write it like this. Mu of x in P such that phi x is bigger than t dt. So you can evaluate this integral along this set just using the indicator when the levels of this function, okay, from 0 to infinity. Because we know this is a non-negative function, okay? So now let's see what, let's try to evaluate the measure of this set, because what we want to prove is that this is finite, okay? This is finite, that's what we want to prove. For that, we just want to check, we will need to evaluate this quantity here, the measure of this set. Let's see that phi of x bigger than t. So because phi is a supremum, so this would imply that phi n of x is bigger than t for n large enough, for some n large enough, okay? Actually, you can find a subsequence that, that realizes this limit, and then you can choose on that subsequence n large enough, so that after which you have this guy is bigger than t, okay? And by definition of phi n x, this would imply that, with that notation over there. So this implies that this phi n x bigger than t would imply that mu of p intersect with qn. So I'm dropping the x, okay? But the dependence of, maybe let me just write it here. This will be less or equal to e minus t mu of qn x, okay? Because, you have the logarithm, and so just from the definition. So this is definition of phi n x, of phi n x. Okay? Now what you can do is this set here, you can make a partition of it using these qn's Okay, we make a partition, we partition this set, the set of x in P, such that phi x is bigger than T by P intersect, so you should be in P already, and Q and JX. Okay? So this is just the subsequent that realizes, or maybe a subsequence of a subsequent that realizes the limit, and then you use the x for which you have phi n x bigger than T, you use that Q, okay? So you can write the partition of this with like this. Now from there you can see that the measure of this set, the measure of the set of x in P, such that phi x strictly bigger than T, this measure will be less or equal to E. So it will be less than the sum of these measures, the sum over J of mu of P intersect Q and J, because this is a partition there of this set. You can write this set as a union of those guys, so use additivity of the measure. So this is less or equal to E minus T times the sum along J of mu of Q and J. This is here. This is this part that you're using here. So, yeah. And this is a probability measure, and these guys are partitions. So this is less or equal to E minus T. Okay, because these are partition. Q and J's, they are different. Their sum is less than the measure of the whole space. Okay. Now let's get back to this quantity that we wanted to see. So we wanted to evaluate the integral of phi d mu. So we see that this is less or equal to, so yeah, I have this. This you can write it, this is less or equal. So from here, the sum along the all partition elements of the integral of mu, sorry, you can see that this is the minimum between E minus T and the measure of P, okay, dt, because you have the measure of this set, the measure of this set is less than E minus T here, the minimum of these two guys. And for that you can write this integral into two integrals, which is when this guy is less than, when this minimum is achieved here and when the minimum is achieved here, which is 0 to minus log of mu of P, mu of P. So this is when mu of P is less than E minus T plus the integral from minus log mu of P to infinity. And here the minimum is achieved, E minus T dt. All right? So when you take this integral, you plug this guy, and for T in between 0 and minus log P, the minimum is achieved here, and otherwise it is achieved there. And you see that this is less or equal to, this guy will give you this first sum will give you the entropy of the partition. And this guy is bounded because this is integral, this is finite. Okay? So this proves lemma 2. Okay? Because integrable just means that the integral is finite. Now there's lemma 4. I hope I will finish today before this proof before. So at mu almost every x, we have, so we wanted to evaluate this limit here. We have that the limit when n goes to infinity of 1 over n, the sum j equals 0, n minus 1, phi n minus j along the orbit of x. These two, they have the same limit. Yeah, this you're evaluating along an orbit, but you're changing this function as a sequence, okay? Here is the same function. But what is crucial here is that phi n we know is converging to c, okay? So that is what we have to use here to prove this lemma. So unfortunately, I have to erase this part. So let's prove lemma 4. Earlier I said 3, but there are 4 lemmas to prove before we get back to the proof of the Shannon-Macmillan-Bryman theorem. Yes. So we want to prove that these 2 pointwise limits are the same. By the way, one could ask, at this stage of the course, we don't have to ask that question that why this limit exists. Because we know Birkhoff, we have the measure is invariant. Birkhoff tells us that this function exists, okay? So first of all, because mu is f invariant, f star mu equals mu, then you have that phi, the L1 norm of phi n minus j composed with fj minus phi composed with fj. This L1 is the same as phi n minus j minus c, okay? L1, because the integral of this will be the integral with respect to, the integral of this with respect to mu will be the integral of the function without the composition with respect to fj star mu. But fj star mu is just mu, so you have the same quantity here. So let's write this as a notation. Ck is the supremum of I bigger than k of Ci minus C. Okay? So this function is converging, so this, we know that for k large enough, this is going to 0, okay? So, and it is easy to see that this guy is in L1 because this will be less or equal to, by lemma 2. So, lemma 2 implies that Ck is in L1, okay? Now let's evaluate. So, we want to evaluate that these two limits are the same. Let's take the difference of the two sums, okay? 1 over n of phi n minus j minus c composed with fjx. Okay, let's split this sum by introducing this ck. 1 over n, j equals 0 to n minus k minus 1 of ck composed with fj. X plus, so I will write is less or equal to plus 1 over n, the sum j equals n minus k, n minus 2, the psi. This is the psi from lemma 2, okay, that we were proving that it is integrable, fjx. Yeah, here I don't need to put absolute values because this is non-negative. This is also non-negative by definition. Let's write this as phi tilde k. This the average of phi k to n minus k, phi tilde k. Okay. So here you can use here the monotone convergence theorem to have that. This so monotone convergence theorem to have that the limit, the integral of limit as k goes to infinity, okay, of psi tilde k. This guy is the limit when k goes to infinity of psi tilde k. This is monotone convergence theorem, and this is just the limit of phi k, okay? The mean which we know it is 0 because phi is converging to psi. Psi n is converging to psi. So for k large enough, this is just the remainder, the tail of, for k large enough, this is small. And we know that this function is non-negative, okay? Psi tilde k is non-negative. Psi tilde k is non-negative. And this would imply that this is the limit, the pointwise limit of psi tilde k is 0 for me almost everywhere. Okay, so let me use some space here. So from there, you can see that the limit of this implies then the limit when n goes to infinity of 1 over n so these two guys, they have the same limit. Okay. And in particular by Birkhoff, so we know that in particular we know that this sum 1 over n j equals 0 to n minus 1 psi what did I do? So this is what I'm going to say. The x, yes. So this guy is converging, which is the limit that, which is the same as the limit that we were looking for. We know that this guy is converging. So in particular, this one also is converging. So this will imply, if I erased it, yeah, I don't have it anymore. So if you remember the expression of minus 1 over n log of mu of p and x, we're having a first term that was something about it. So I should have it here. I have it written somewhere here. Yes, here. Yes. minus 1x plus 1 over n phi n minus j at fjx. So we know this one will have the same limit at this, okay? And the fact that this limit exists is from Birkhoff. The fact that this limit exists is from Birkhoff ergodic theorem. Birkhoff theorem. I don't know if I should say Birkhoff ergodic theorem. So this is the fact that the limit exists. So let's get back to Shannon-Macmillan-Bryman theorem. So from lemma 4 gives that, these two, they have the same limit. So in particular, this limit exists. The first guy exists, which is this one exists, and this is going to 0. Because this is bounded away from 0. Okay, so you would have that h mu f px. This guy is phi tilde, which is this one. And this is from Birkhoff theorem, okay? This is the phi tilde from Birkhoff theorem. And the potential we use here was the limit of these phi n's. The limit of the phi n's, okay? So this is Birkhoff. And this convergence is also L1 because we have it here. So, the fact that you can use dominated convergence theorem if you want. You have pointwise convergence and domination. So this convergence will be L1. And Birkhoff, again, will tell you that the integral of h mu, which is the integral of phi tilde x, px d mu, which is the integral of phi tilde d mu x, this is this limit. This is the limit when n goes to infinity of 1 over n, the sum of phi n minus j if jx. And this one is this, which was the entropy, which was the definition of the entropy of the partition. Okay, this guy will be equal to the limit when n goes to infinity of 1 over n h mu of h mu, the entropy of the Pn's partition, and this is just h mu f. Yes. So this is another tool to calculate the entropy, and it gives a refined version, like to see the entropy as a function, okay, depending on x, and the integral of this function will give the total entropy with respect to the measure. So I will stop here for today. So the next lecture we will go to topological entropy and variational principle. Okay, so I will stop here for today.